Another important topic is to expand on linear independence and what's going to form what we call a basis in our space. So we should know from before that two or more vectors are linearly independent if a linear combination equaling to 0 only has the trivial set. We say that they are linearly dependent otherwise. So if there is another vector C1 to CP, in which when you do this linear combination, you end up getting the 0 vector, then there must be some type of linear dependence between them. If this set of vectors, okay, 2 or more, are linearly dependent, then we do know that there must be some type of linear combination in which you can get one of the vectors in terms of the other ones. So basically what that means is you can write like Vj equals 2v1 minus 3v2 plus and you end up getting one of the other vectors in this set. So the general difference between linear dependence, just that we talked about before, and in the vector space is that vectors are not always in tuples. So homogeneous equations cannot be written as a system of n linear equations. It might be a little bit more complicated than that. So the vectors cannot be made into columns of matrix A to study AX equals 0. So we must rely on, okay, we can set up this set of vectors where one vector is equal to a linear combination of others when we are in these vector spaces, because it might not just line up so nicely with matrices that we've done before. Now this brings us to the definition of a basis. So we are going to say let H be a subspace of vector space V. A set of vectors B in vector space V is a basis for H if the following two things are true. Number one, B is a linearly independent set. And two, the subspace spanned by B coincides with H. Or in other words, H is equal to the span of B. Some examples from the textbook on this. So if we let A be invertible, okay, so A inverse exists, then the columns of A do form a basis because they are linearly independent. Think back to that whole list of invertible matrices theorem. So because if A inverse exists, then all of these column vectors must be linearly independent. If I have linearly independence, then I know that these columns are going to form a basis for Rn. Okay. All right, let's look at kind of like the three-dimensional space. So if we look at the figure is for R3, which I think is really helpful to look at, but if we have essentially like the column vectors of the identity matrix, so we're going to call them E, kind of like for the elementary matrix, kind of. I mean, elementary matrices have a different thing, but we like to call these the E's to kind of signify something similar with the identity matrix. So the set of those E vectors is the standard basis for Rn. They are all going to be linearly independent because they only have one in the space that is the same as like the number for the column vector. So like E2 has one in the row 2. Okay, En has a 1 in row n. And so they have to be linearly independent, and any space in Rn can be written as a linear combination of those vectors, E1 through E whatever. You just put in your multiples here, and so therefore it is a span, and it makes a basis for Rn in that case. All right, here is another example where we will be writing this out. So let V1, V2, V3 be these vectors, and is this a basis for R3? Well, since we need to make sure that they are linearly independent, one thing that we can do is see if A as a combination of this vector space has an inverse. So we can use a couple of the different methods to do so. The method that I would choose to use is to augment this with the identity matrix and see what you get with row reduction here. And after doing all the row reductions, you end up getting 1, 7, 5/3, -2, -9 and 1, and then 1/3, 15/6, so divide by 3 5/2, and then 1/6. And that's not so much important what these numbers are, other than the fact that just A inverse exists, right? So what do we know then? We know that V1, V2, and V3 are independent based on just that fact alone. So the fact that A inverse exists, then the column vectors must be independent. And so because I have independent vectors, they are going to end up spanning, because it's a 3 by 3, spanning R3. And so yes, this does form a basis for R3. All right, one more example just to chat about here. Let's say that S is the polynomial set. Verify that S is a basis for Pn. Well, just so that we know, if you have T, sorry, my stuff froze there, T squared, there is no combination that can happen if you were to take a number times T plus any other number times 1, right? There's no way for us to do a linear combination of other polynomials to get that polynomial, which is why it's important for us to have that second definition that we had. We can't do this in the same vector space way that we did before with the column vectors. Here we need literally to be like, any of these polynomials can't be written as linear combinations of the other ones. So all of these pieces are going to end up being linearly independent. And one thing is, like for Pn would end up being something like C naught times 1 plus C1 times T plus C2 times T squared, all the way up to Cn times T to the n. So Pn is a span of each one of those polynomials, and they are all linearly independent. So yes, S is a basis for Pn.